Hi, everybody. We're beginning chapter two, combinatorics. Uh, I just want to, look at this poem here. It's just kind of interesting. They always put in some cute little thing here. So it says, enumerative combinatorics date back to the first prehistorics, who counted relations like sets permutations. To them, were part cult, part folklorics. And it's interesting to say part cult. Um, that's really what I found interesting about this is that nowadays we generally, or at least here, here in college or me or whatever, we generally think of math as something that's, crunch out numbers, get an answer, prove a theorem, and so on and so forth. But back then, even a little bit now, but back then, um, math had certain philosophical ramifications, religious ramifications, um, spiritual ramifications, all sorts of ramifications, which we don't generally know. We today we think of math as generally as a secular subject, and I just found it interesting that this idea, uh, part cult, part folklore. Anyway, that's me. Now, getting back to chapter two, let's start with section 2.1. That's what we're doing today, 2.1. Basic counting techniques, the rule of products. Okay, so combinatorics, how many lunches can you have? A snack bar serves three different beverages, uh, and five different sandwiches. And is that it? Okay. How many different lunches could you have? Well, the simple way to do this is to make a tree diagram. And you could have five different sandwiches: bologna, ham, cheese, chicken, or beef. And then there are three different beverages: milk, coffee, tea. So you can get bologna and milk, bologna and coffee, bologna and tea. That's three guys right there. Um, ham and milk, ham and coffee, ham and tea. And as you can see, what you wind up doing is just multiplying 5 times 3. And that's really that really is the rule here, which is we multiply. So if you have A as a set, A, B, C, D, E, it's 5 elements. B is a set 1, 2, 3. So if you want to know all the different elements in the cross product, we have A1, A2, A3, da da da, and that winds up being 5 times 3, 15 different elements. That's why on a true false test, you have 10 questions on the true false test. Well, that the true that diagram will be true false, true false, true false, true false. It winds up being 2 times 2 times 2 times 2, 10 times. Why 10 times? Because there are 10 questions on the test, and that's as you know, it's 1024. As long as I'm saying interesting little tidbits. I think I mentioned this in class, but I don't remember. Oh, wait, we don't have class. This is all online. Anyway, um, the when you talk about a kilobyte, so we say it's 1,000 bytes, but a kilobyte is really not 1,000 bytes. A kilobyte is really 1,024 bytes because it's 2 to the 10th power. Because as you know, computers tend to be in powers of 2. Why are they in powers of 2? Because they're based on switches, and switches are either on or off. So there's only two options. So you could have multiple switches, get multiple different powers of 2 and so forth. But basically, because of the physical way a computer works, on and off. That's it's all based on choices of 2, which becomes powers of 2, which becomes base 2, binary, or the whole smack. Anyway, let's move on. The reader is encouraged to visualize the tree diagram, but not to draw it, because it becomes very unwieldy if you try drawing this after a while. And that is the rule of products. That's what I'm saying. It's the rule of products, which is that we multiply this stuff. And let's see. And it could be more than two operations. For example, if a questionnaire contain so the rule products can be extended to include sequences with more than 2 operations. If n operations must be performed, the number of options, blah blah. Right. So if you have two, 5 sandwiches, 3 beverages, and 2 desserts, so that's gonna be 5 times 3 times 2, so on and so forth. Anyway, That brings us to a concept we had before called power set. We mentioned that power set is the set of all subsets of a set. So if I have the set 1, 2, 3, so the power set will include the empty set, the set 1, the set 2, the set 3, the set 1, 2, the set 1, 3, the set 2, 3, and the set 1, 2, 3, which is 8 different things, which is 2 to the third power. So why is it 2 to the third power? Well, if you think about it, if I'm building a power set, every element either is or it, if I'm looking at a subset of my big set, and I want to how many of these subsets could I have? Well, every element either is or is not an element of that subset. So each element has two choices. So this one's being 2 times 2 times 2. So if you have, if you have 3 elements in the set, so one's being 2 times 2 times 2, that's the possibilities, and that is the story. And of course, we're only talking about, notice we're only talking about finite sets. There was a great mathematician named George Cantor who extended the idea of this to an infinite set. Um, and that's kind of cool and awesome. So, and he did amazing things with this. Okay, well, that was section 2.1. Hope you enjoyed it as much as I did. And that, my friend, is the story. We'll see you guys next time. Bye.